Hello everyone, this is episode 2 from Extreme Loading for Structures Software. In this episode, we are going to speak about the applications that you can use ELS for, the graphical user interface, how to create models, and also we'll be speaking about blast analysis, and we will be doing a small example for a building, and we are going to subject it to a blast loads and finally, how to navigate through the results inside ELS Viewer. Let's start by going through the applications that the ELS is capable of doing. As you can see here, the naming of the software is extreme loading. This means that we work in examples or in engineering applications that speaks about applying extreme loads on a building. Extreme loads like, for example, the anti-terrorism force protection applications, like the blast analysis, as well as the progressive collapse analysis, also known as disproportionate collapse analysis. The second application is forensic engineering, when you have an example for a building that an accident happened inside it and you want to investigate why this accident happened. Then we have also the seismic analysis, either it is a time history analysis or a pushover analysis. Wind analysis, of course, either static or dynamic. Fire analysis, corrosion analysis, and finally projectile impact analysis. Let's start first with the graphical user interface. This is what we call the graphical user interface of ELS, where you have some menus over here. You also have some toolbars to help you in creating models. You have here what we call the browser, where you can navigate through different levels of your structure, the materials that you are going to use, and also the properties of each component you are going to model. Um, the kind of modeling inside ELS or components that you can model inside ELS, starting from RC columns with its reinforcement details, circular RC columns, brick walls with whatever bonding that you might have, RC beams with pre-stressing if you want to add pre-stressing. And this is an example for a building that was fully constructed with ELS applications. Going through the steel components, you can model, of course, all the AISC databases, and all they are all inside the software. You can model connections like RBS connections. You can model cold formed steel corrugated metal decks, as you can see here, or studs with its connections like the screws and so on. And this is an example for a full steel building that was constructing using ELS. We also have inside the technology some templates to help the user build models quickly, like flat slab buildings. We also have for the trusses this template to construct a tower like this, or basically a simple truss. You have also here a template for the hollow core slabs with its pre-stressing. And finally, segmental bridges, where you can model a segmental bridge with its reinforcement and its pre-stressing as well. The first application that we are going to speak about today is the blast analysis. And in this example that we see in here, we are going to speak about how we generate blast loads inside ELS. The first way of generating blast loads is using the UFC code, UFC 33402, where we programmed the charts here to get to be able to get the pressure, the duration, the impulse, all the data required to do the blast analysis. And in this case, the user just put the bump weight, the bump location, as well as the explosive types. And when you click on check, you get here the information for your blast, like the arrival time, the duration, the peak pressure, and so on. We also uh, created an example for this case where you can see here the Oklahoma building that was bombed back in the 90s, where you can see here how close are the results of the ELS compared to what actually happened inside the field itself. The second way of getting blast pressure is that you can import your own blast pressure inside ELS. If you have your own blast pressure, we give the user the ability to import it as uniform pressure at some elements. And as an example in here, you can see an RC column subjected to a blast load. In this case, we modeled the reinforcement rebars as elements, as a solid element, where you can see here the debris falling and the permanent deformations happened on the column due to the blast load. The third way for importing a blast pressure is by importing CFD analysis. We created a tool inside ELS to be or to allow engineers to import CFD blast pressure inside ELS from OpenFOAM or BlastFOAM, and these are open sources for doing CFD blast analysis on a building. As an example, you can see here this building, we solve it first on the open form to be able to get the blast pressure, and we can see here the distribution of the blast pressure along the face of the building, the sides of the building, as well as the roof of the building. This chart is showing the blast pressure wave. So you can see here the positive phase and the negative phase for the blast loads. Of course, when we are doing blast analysis, you don't have to assign plastic hinges because plastic hinges are formed automatically. A strain rate effect is considered automatically inside ELS. You can get stress and strain output as well as internal forces diagrams. And by the way, ELS is the only software available in the market that is using solid elements and still gives the users the ability to generate internal forces diagrams like bending moment, normal forces, and shear forces. Let's start now by modeling an example using ELS. In this example, we are going to model this building. It's a very small building, 4 columns, 4 beams, a slab, a masonry wall, and a window glazing inside this masonry wall. The blast pressure applied is zero point 0.1 kip at the center of this room. The the distance between the columns here are 200 inches in both direction, and the height of the column is 150 inches. This is the cross section of the column, 12 inch by 12 inch, with reinforcement rebars 8, number 5, and 3 branches of stirrups in each direction, so number 3 at 8 inches. The girders are 12 inch by 30 inch, and it has bottom reinforcement of 4, number 5, and top reinforcement as 2, number 5, and it has also stirrups number 3 at 8 inches. The slab is 5-inch RC slab with top and bottom reinforcement number 3 at 8 inches. Now let's start by opening ELS. We will be now seeing the first screen that appear when you start the application of the ELS. In the first screen that you see in here, you put the project name, the first level height, as well as the height of the first floor. In our case, we are working with units inch, so I'm going to choose here inch for the length and mass as kips and angles as degrees. Of course, you can see here that we have list here of units, feet, inch, meter, centimeters, and millimeter. And as for the mass, you have kips and the pounds and the tons and the kilograms. I will use the kip and inch. And let's start here by defining the level height, which was the first level height, 150 inches. Now click OK. This will open up the main modeling window inside ELS, where you can see here the menus like File, Edit, View, Draw, Modify, Templates, Tools, and so on. You can see here some toolbars also for creating or for modifying. You can see here some toolbars for creating drafting like lines or rectangles or circles or arcs and so on. You can see here also a toolbar for creating styles, and we will speak about the styles later on, but this is mainly how you draw components inside ELS. Also, you have here what we call the browser. This is a very important area that you will use a lot when you are trying to model the building. Inside ELS, you can model either in the 2D view, like the XY plane, as you can see in here, or in any other plane, like the 3D view, as you can see in here, or an elevation view or a side view, as you wish. Let's start first by defining this area, which is the grid. Actually, inside ELS, the need of the use of the grid is very minimum, unlike other FEM software where you have to define a grid to assign some joints or put some boundary conditions at some locations. Here inside ELS, the use of the grid is just something to help you, but it is not necessary to have a grid in your modeling, as you are going to see now. Let's start by modeling the building. The building that we have seen it before. We are going to model the first component, which is an RC column. Going to the styles. In the styles, you will find styles for columns, circular columns, girders, slab, reinforcement rebars, walls, windows, 8 nodes or a general object, and finally the general steel sections. Let's have a look first on what is a style inside ELS. A style for a column, for example, if we click on column style number 1, this will show the geometry, the reinforcement rebar inside this column, as well as a steel section if you have a composite member, meaning that you have a concrete reinforcement and then a steel member embedded inside this concrete. For now, we only have geometry and reinforcement, so we'll use the steel section as none. Let's go to steel section or the geometry first. So the geometry of the column, you assign here, if you wish to change the naming, of course you can change it. And you can define here the width of the column, the depth of the column, as well as the material of this column. Of course, we have a library of materials that we are going to discuss later on, but we will be choosing this column or the geometry of this column to be a normal concrete. Apply and OK. Now we are going to go to the reinforcement rebars. In the reinforcement rebars, you can put here the cover of the reinforcement. So we will assign the cover as 2 inches. Now we need to assign 3 bars in each direction around the column. So in direction 2, 2, which is the green arrow in here, you can put here 3 bars with an area as we have seen in the example of number 5. And in the direction 3, which is this one, we need to put 3 bars. But because we are considering the corner rebars in direction 1, so you need to exclude the corner rebars from this number. This means that instead of putting 3 bars, I will only put 1 bar with the area that I'm going to choose, number 5. And the material is normal steel as you have seen in here. Now let's go to the stirrups. We have seen in the example that we have 3 branches of stirrups in each direction, spaced at 8 inches with an area of number 3. And apply and OK. You can see here a preview for the geometry as well as the reinforcement rebars inside. Now let's go ahead and insert the column inside the modeling window. So I will go to draw a column and let's put the column anywhere inside the modeling window. We can see here that ELS comes with a default mesh as well as the reinforcement inside. It is shown in the yellow color in here. We can select one element from here, then we go to the properties. In the properties, it will show you the name of the style of the column as well as the height. If you need to change the height from here, it can be changed from here. And by default, the height of the column is considered as well as same as the height of the first floor of your building. So by default, it is 150 inches according to the information that you put at the first screen. Then you can define from here the meshing, how many elements in each direction. To be able to see the meshing in a better view, you can change the view if you go all the way down to element group specifications. You can change here the display mode to be solid and shrink, where you have a better view for the elements to be able to see how many elements you want to put inside ELS. Um, I'm going to show you another way for showing this as a solid and shrink, but this is applied on all the components inside the modeling window. If you click here on this icon, solid wireframe, it will change it to be solid or wireframe, as well as shrink elements to be able to see the elements shrinked or not. Now let's go ahead and select another element, and I'm going to define the meshing inside ELS. The meshing inside the column, so I'm going to select, if I have this column as 150 inches, let's assume that the number of elements along the height of the column is 30. So I've assigned now 30 elements, and in each direction, uh, in the width and the depth of the column, I'm going to put 3 and 3, as you can see in here. Now we have finished the first column that you have. I can take a copy from this column. Just simply right click, copy from anywhere. Let's select the midpoint of the column, and I will put here at a distance of 200 inches and 0, which is the distance between the, the columns that we have. And we have another column style in here, which is the same exact style as this one. If the user wants to change the style here or put another column inside the modeling window, all what you have to do is to go here to styles, and you can change the style to any other style available in the style screen, as you can see in here. So we have column style 1, 2, 3. Each one of them is holding some information about the geometry as well as the reinforcement rebars. I've clicked now undo or control Z, and if the user wants to put from the beginning a different column style, like a column style number 2 here, which has information for 20 by 20 for the geometry and some other reinforcement rebars, just go to column style number 1, set as default, and now when I click on the column, it will be a different column geometry, as you can see in here. And going to the properties, you will be seeing here column style number 2. Now let's click on undo. I'm going to create now the girder joining between these two columns. With the same exact steps, go to styles, girder, girder style number 1, and I'm going to change the geometry to be 12 inches in width by 30 inches in depth with a material of normal concrete. And for the reinforcement rebars, I will put here the bottom reinforcement as for number 5, and the top reinforcement I will assign it as to number 5. And for the sidebars, which is at the mid location of the girder, I will just assign one bar with an area of number 3. And all of these has a material of normal steel. Now for the stirrups, I will only put 2 branches in each direction with a spacing of 8 inches and it has an area of number 3 and a material of normal steel. Apply and OK. We don't have a steel section, so we'll choose here none. Apply and OK. Now it's time to model the girder. With the same exact steps, go to Draw Girder and select the mid location of the column to the mid location of the other column in here. Now let's do the same steps. Go to Properties, and in the properties in here we can change the number of elements in each direction. Let's assume that we have let's say 25 elements along the length, one element along the width, and five elements along the height. When we can see it also, if we change here the view to be solid and shrink, you will be able to see the elements that we have. Please consider this, that by default we have extension for the reinforcement rebars from the girder inside the column. So if I choose to move this column, I'm just moving it for the demonstration, you will see here that we have extension for the reinforcement rebars. Perhaps if we bring an elevation view, you see here that we have extension for the reinforcement rebars inside any component. And the length of this extension outside the boundaries of the beam can be defined from the reinforcement area inside the browser in the properties. So you can see here the reinforcement extension at the start and at the end. And if the user also wants to change the extension of the stirrups, he can do so as well. So if I click now on the start extension for the stirrups at 12, so it will be extended 12 inches beyond the boundaries of the beam for the start and for the end as well. For now, I'm going to click on undo, keeping everything by default. And let's start by creating the other frame for the room that we have. So I'm selecting here all the elements, and you can either use a copy command or array. For now, let's use an array. So you can put here the number of items in each direction, X, Y, and Z. In our case, we are using the Y direction. So put 2 copies with a distance between them as 200 inches and click on OK. You can see now that we have created another copy from the column in here, or the girders, sorry. Now let's close the room by adding more beams here. So I'm going to add the beams. We can take a copy from this beam from the end of the column in here to the end here. And if I wish to change the properties and the meshing for both beams, I can select one element from this beam and press on Control on the keyboard and then select another element from the second beam. Then we can assign the number of elements in each direction as we can see in here. With the same exact concept, we can change here the view mode to be solid and shrink. Now it's time to model the slab in our analysis. The slab that we have is 5-inch thick slab. So I'm going to the slab here, slab style number 1. And we are going to define the geometry or the thickness of the slab. It is a 5-inch slab. Apply and OK. And for the reinforcement rebars, we have one bar spaced at 12 inches on center for the top and the bottom. And also it has an area of number 3, as we have seen in the slide that describes the model that we are going to be creating now. Apply and OK and OK. The best way to model a slab is through the 2D view to snap on the corners of the building. So I'm going to go to Draw Slab, and we are snapping on the internal components or the internal columns, 4 locations, then right click. So you can see that we have modeled the slab right now, and it has reinforcement details inside. Later on, I'll be showing how to add reinforcement, uh, not like a top and bottom shell of reinforcement or a top and bottom mesh. I'm going to teach you how to model a custom reinforcement to account for like the extended reinforcement at a continuous slab. If you have like a continuous slab in here and you don't want to put a top rebars at the middle region of the slab, I will be speaking about this at different episodes from ELS. Now let's go to the properties. Same exact thing. I'm going to change this view to be solid and shrink. And let's assume that the number of elements in each direction 30 by 30 by one element through the thickness. Now we have finished now modeling the structure components. Now let's move to the non-structure components, which is a masonry wall in here, and it has an opening for a window glazing that we will put inside this masonry wall. Go to the styles, and in the styles we'll go to walls, wall style number 1, and in the wall geometry you assign the thickness of the wall. Let's assume that the thickness of our wall is 6 inches and it has a material of brick with a mesh generation of masonry, and I'll be speaking about the mesh generation masonry later on in this video. When we click here on the basic information or the brick information, so you put here the length of each brick, the height, as well as the width of each brick. Then you assign the mortar material that's going to be in between those bricks. Apply and OK and OK. Now we go to the toolbar to draw a wall. Drawing the wall is from the center of the column to the center of the column in here. And now we can see the modeling or the model for the wall that we have. We are going again to change the view to be solid and shrink, and we can see here the model of the wall. Please note that now there is an intersection in between the beam and the wall. If we want to check this intersection, if you click here on check integrity, you will see here that there is a girder that is intersected with a wall. Of course, you can make the intersection automatically in here, but I prefer to adjust the height of the wall to be just underneath the beam. So in this case, we have the beam as 30 inches in depth. So what I need to do is to reduce the height of the wall to be 120 inches instead of having, I'm going to select one element from here and then change the height to be 120 inches. Now let's go ahead and have or insert an opening. Inserting an opening in here is as easy as create an opening. You can see here that click on add opening, it will add an opening here inside the wall. The opening, you can control the opening upper distance, lower distance, left distance, as well as the width and the height of this wall. By default, the width and the height of this opening is adjusted same as the width and the height of the window that is in the default inside ELS. So if I go here to structure, to styles, and in the styles you go to window style number 1, you can see here the geometry. So the geometry is 32 by 45, as you can see, and then you assign the thickness of the glazing that you have as well as the thickness of the mullions at each location. Click apply and OK, and now I'm going to click on the window, select a window from here, right click, move and this time I'm going to snap to the elements. So I'm snapping here on the mid point of the mullion and move it to the mid location of the wall. Let's put some meshing. So I'm going to properties, and in the properties, let's choose, for example, that we have a 500 elements inside this modeling. Now let's go ahead. We have finished now the model. Let's have a look on the materials first, and then we will go to the loading and assign the loading. These are all the materials that we have inside ELS. The first one is a linear material, and this is not elastic. This is a linear material up to failure. Then you have here a concrete material model, steel material model, bilinear material model, mortar material model, bearing or compression only material, tension only material, brick, glass, aluminum, and a tension only bilinear material model, and as well as elastic material model. Finally, you have here what we call the user-defined material model, and we are going to speak about this at later episodes. Let's go to the first material. So the material that we have here is normal concrete. You can assign here the Young's modulus, the shear modulus, the specific weight of the material, the tensile strength as well as the compressive strength of the material, and finally the shear strength of the material. And if you click on plot stress and strain curve, you will be able to see the backbone curve of your material model. With the same exact concept, if you go to the steel, so you assign the Young's modulus, the shear modulus, the specific weight to account for the mass as well, the yield strength of the material. Let's assume that it is a 60 KSI steel, and you also assign the ultimate strain, the ultimate stress as factor from the yield. So if this was like a 75 KSI as ultimate, I will put here this factor as 1.3 and then click apply and OK. Now we have assigned the materials. Now it's time to assign the loading. If you go to the loading scenario here, you have an icon for the loading scenario. The first stage of loading is always kept as a static stage to account for the own weight. In this case, we are considering only the own weight, so the dead loads. So we are applying here the dead loads as a loading increment on 10 steps. Then we will be adding new stage of loading to apply the blast loads. So it is a dynamic stage with a load of a blast load, and in the blast load I'm going to put here the the time step, and the time step should be something very small because it is a blast analysis. Let's assume that the time step is 0.0001 second. This is the time step, and we have also an output time step. So output time step, I will try to match it with the input time step to be able to see how many or to see the output at every time step from our analysis. Apply and OK and OK. Now we have set up the loading scenario. It's time now to define the load of the blast. Go to loads, and in the loads here we assign the bomb weight. The bomb weight is 0.1 kip, and the bomb location, we need to pick a point inside our room to be the source of the blast load. So I'm going to get a plan view, get the the midpoint of my slab, and then I'm going to reduce the heights because it is snapping on the roof of the building. So 150, let's assume that it is in the middle of the room, so at 75 inch. And then you have here the explosive types, either TNT or C4 or whatever material. Then click on check. The check will give you the arrival time, the duration as well as the peak pressure, and close, then apply and OK. Please note that by default we have ground here, so we don't need to define boundary conditions because these columns and these walls are extended. There are springs that are generated with the ground to extend the material inside the ground as if you are having a foundation. And the material of the ground can be defined here from the analysis settings, ground and boundary conditions. So we have assigned here the ground material as a concrete material. And so now we don't need to assign any boundary conditions. If you want to assign different boundary conditions, all what you have to do is to remove the ground, and you will be able to put whatever boundary condition, and we'll be seeing different boundary conditions at different episodes in the next few days. Now we are ready to run the model. Just click on run analysis. It will ask you if you need to check the integrity, like if there is any intersections between the components. We don't have intersections, so we are good to go. The solver is going to start now. So we are at stage 1 of loading, applying the on weight. Now we are in stage 2 of loading. The good thing about ELS is that you don't have to wait until the analysis is done to be able to see the finished steps of your analysis. So I can go ahead and open the viewer. I'm going to open the viewer now to see the finished steps of our analysis. This is the viewer where we are having the ground, as you can see in here. If I need to play the results or see the finished steps so far, just click on play. We see here that the bomb or the pressure arrived here to the area of the window, and the window is the weakest location of your structure, so that's why we are seeing here damage and deformations. And when you reach here to the rust frame, if you click on update, you'll see that more information is sent to the viewer to be able to see what's happening. So the first thing that we can see inside the model, the cracking. So it, even before showing any cracking, we can see here from an elevation view the cracks that are generated inside the brick wall. By the way, by default, all the springs generated between any masonry wall and any structural component is a mortar material. So this is by default unless the user wants to change this, and we will be showing it later on how to change the interface materials. We can update the results once more. The first thing that we can see here, besides the cracks, I will be showing you different ways to show the cracking, but let's first see the blast pressure distribution on the building. So if we go to contours, blast pressure settings, we can calculate the pressure on all the frames so far to get how much pressure that was measured. So we can see here that this is the maximum pressure that the building seen. Apply and OK. Perhaps we can remove the ground because it is an internal blast pressure, and I'm going to get this in or rotate this around the x-axis, and then we can play the video from the beginning to see the distribution of the blast along the history. So we can see here the distribution of the blast. Perhaps we need to go with as a frame by frame. So I'm going to move it frame by frame. So we have seen the blast pressure wave. Now, second thing that we can see is the cracking, and this can be shown if you go again to the contours. And in the contours, I'm going to plot now a stress or plot the principal strain, because this is the best way for viewing the cracking inside ELS. Of course, we see here that the strain is very high because of the damage that's happening inside the window. So I will just put a number. Let's put zero point 0.1, apply, and OK. We can see here the cracking happening around the window. Then the propagation of the cracking and the diagonal cracking that's happening in the wall. As you can see here, there is cracking happening between the column and the wall, because as we said, this is mortar material by default. Let's bring the final frame so far. It's still solving. We can see here an initiation of a shear crack inside the beam. Perhaps we can view it or try to increase the value of the strain. We can see here shear cracking happen in the beam. Another thing that we can get it from here, if we close the contours, if I need to plot, for example, a chart for the deformations happening in the slab, this can be done by selecting one element from the slab. On the x-axis, I'm going to put the time, and on the y-axis, I'm going to select element displacement in z direction. Pick one element at the middle, click enter, and OK. We can see the deformations happening, and when you click on update, it automatically updates the value of the deformations. We can also get from here, we can see the damage visually now happening in the slab, as well as the shear failures that's happening in the beam. One other thing that is good to see is the internal forces inside those beams. So I'm going to select an element from each beam, then go to the properties to be able to display the moment on those beams. So M2. And let's go ahead and play the results. Let's hide the elements to be able to see um, the information or the bending moments in a better way. This is the bending moments happening inside the beam. You can see the uplift happening because of the deformations or the uplift that's happening in the slab due to the blast load. And you can also see here that if we click on show envelope, it will bring you the maximum and the minimum values for the bending moment so far. And when you click on update, it keeps updating the results that you have. We can view back the structure by going to view elements. One other thing that you can see in here, if I need to see, for example, the stress and strain curves for the reinforcement tree bars at one of the reinforcement tree bars inside this slab. So how do we know the elements or the springs that yielded? The ELS has a very good tool that's called in the preferences. You go to read spring states, where you can see or visualize the separated springs or the springs that are still in the elastic range or the yielded or the springs that are in tension or in compression or a tensile failure or a compressive failure or just a cracking. Click on OK. And now let's bring a plan view because we need to see what's happening in the slab. So I need to view the slab in a wireframe mode, then show here the yielded springs. All the springs that you are see, or all the lines, mm, the blue lines that we can see in here, all of these are springs or reinforcement rebars that is yielded. So we can go like few frames to the back in here, then select some springs. I'm going to select here, for example, this spring. This is a top and bottom reinforcement rebars. So I'm going to plot here a relation between spring and strain versus stress, and click OK. So we see here that it went to the hardening. One of them went to the hardening and then failed, and the other one probably failed due to shear failure in this spring. I think now we have covered most of the things, most of the information that we show for the blast analysis. In later episodes, I'm going to show you how to remove structural components while the analysis is running. But what you see in here, that this is the damage that we got so far, and probably this analysis is going to take like 15 minutes more until we reach to like 1 second duration. But we will stop for now and see you next time. Thank you.